So Bismillahirrahmanirrahim. This is the lecture. We are talking about the filter design. We'll start with analog filter design, and we already talked about the Butterworth filter design to some extent. Today we'll try to extend the idea of the Butterworth filter. So this table shows for different order of the filter what are the pole locations. So we need to derive the pole locations. So whenever we have derived the pole location for different order, so those are the order. This is for the first order, for the second order, third order. So we can take it, this value. All the values are for omega c is equals to 1, omega c equals to 1. So conventionally this is this value of the omega c is more than 1. So then we can convert these polynomials or the location of the poles accordingly. So whatever the value we have, so we can change this value accordingly. Okay. So previously we have designed our pole and design our filter based on the value, where all the values are given like this. Let me show the examples. We are taking the number like this one. So where we have the value 0.9, that is the amplitude passband gain, and value of omega is equals to 100 radian per second. Now in the second case, we are representing all those values. The gain values are represented by dB. So rather than putting the value in the gain value like 0.9 or something like this, now we are putting all those values are in dB. So the formulas are the same, just we are taking all those values are now in dB. So the process and the formulas are similar. Okay, the process and the formulas are the similar. Just we have dB calculations. So step number 1 in the previous cases, we need to let me check. So there are some sound I found. I'm not sure from where. Yeah. Okay. So at the very beginning, we have the equation. This is the fundamental equation. And since we have two values, omega equals to omega 1 should be given and omega equals to omega 2 is given. And for that, we should know the gain of that particular omega 1 and the gain for particular omega 2. So that is one is for the if we talk about the low pass filter, so we need to think about the cutoff, the frequency values. We are mentioning the value of omega 1 and omega 2. Sorry, this is omega 1 and this is omega 2. Based on that, the cutoff frequency will be calculated. Omega c will be calculated, and also the order of the filter will be calculated. So that already been discussed in the last day. The same thing we have done here. So we have two equations. From those two equations, we need to find. So this is the fundamental equation from which we can find both the value of n. So first of all, we found the value n is equals to 5. The actual value could be very close to 5. So that's why 4 point something, we make it a 5. And based on that value, we can find what is the value of omega c. So the same principle. So I believe that you can understand, and we can move accordingly. So whenever we found the value of n and omega c, then we need to follow the same process. What is the second step? The second step is we need to find the pole locations. And if this is a even function, based on even function and odd functions, so how to find the pole location. So we have already discussed in the last class. Now try to understand that we are designing analog filter. So and of course this is a active element. We need to design an active element to get the gain properly. So now proceed to design a required active analog filter. So we need to design an analog filter that will purpose our service. There are different structure, and Shalen and key structure is one of the famous structure for this kind of filter. To analyze the Shalen and key filter, okay, so in the appendix they are giving some guideline. I also have some guidelines, so I prepared some guideline for Shalen and key filter. So this is an extra node, so I'll provide the extra node. So starting from, so what is our topic? Our topic from moving to the extra page, that means how this topology work and why we are taking the Shalen and key active filter. Why not the passive filter gives us the Butterworth filter, the advantage of the Butterworth filter. So why we need to go for the active filter? Those are the questions. Okay. So why we are using the Shalen and key structure? Let's say we start with a passive filter. So we already know about the characteristics of the passive filter, so how they works and everything. So the transfer function output over input, transfer function output to the input is equals to this one, 1 over 1 plus RCS, where S equals to J omega. S equals to J omega. So this is in the Laplace format. We can write in the Laplace format. So this is a first order filter. So if we move to the second order filter, if we can design a second order filter by cascading to first order filter, then the equation can be written as this one. So this is very easy to compile the equation. The transfer function is now this bulky equation where the denominator is a second order polynomial equation where the highest order is 2 of the polynomials. Comparing this ugly equation with the general format of the filter. So this is the general format of the second order filter where the k omega 0, where omega 0, if we compare these two equations, this is equation number 1 and this is general equation number 2. If we compare these two equations, we found that omega 0 equals to 1 over root over R1, R2, C1, C2. Because this is omega square and this omega square is equals to this one. So this is the format. So how we can put the general format of the equation. So we found that this omega 0 is equals to 1 over root over R1, R2, C1, and C2. This is the cutoff frequency. So omega 0 is the cutoff frequency. The cutoff frequency of the second order filter is let me maximize. The cutoff frequency of second order filter is different than the first order filter. What does it mean? If I have a first order filter, let's say this is a Butterworth first order filter, the second order cutoff frequency. So where is the cutoff frequency? Let's say this is the cutoff frequency, omega c, for the first order filter. Now, if you increase the order of the filter, maybe the cutoff frequency could changes its position in this way, or when you change the order of the filter, that means the cutoff frequency will changes their positions. It might be shifted to the left or it might be shifted to the right. Whatever the case, the cutoff frequency of the second order filter is different than the first order filter. But this is problematic. So what we want when we are introducing higher order filter, our concept is, if this is a low pass filter and if this is the cutoff point, the cutoff point should be fixed. The cutoff point should be fixed, but that will be more steeper than the previous one, or it can be more sloper than the previous one. But we want to make the cutoff frequency constant. We want to make the cutoff frequency constant. That is one of the prime target to design a filter. So if the cutoff frequency changes, that makes a problem. And this is problematic thing due to the passive element in the filter, passive element of the filter. So if R1 is equals to R2, that means in the previous case, in this case, if R1 equals to R2 and C1 equals to C2, in that case, the cutoff frequency is equals to the actual cutoff frequency equals to 1 over twice by RC, or you can say omega C is equals to 1 divided by RC. 1 divided by RC, what we already know that. So if and only if both of the first order filter has the same amount of resistance and the capacitance, then only you do not have any shifting of the cutoff frequency. Here the cutoff frequency are the same for first and the second order filter. So only if you are choosing the both value R1 is equals to R2 equals to R and C1 equals to C2 equals to C, then only the cutoff frequency will remain fixed. So, however, if R1 is not equals to R2 and C1 is not equals to R2, in general, the cutoff frequency of the second order filter can be written like this one. So the cutoff frequency with respect to the first order cutoff frequency. So this is the first order. This is for the first order. So this is for the first order cutoff frequency. So how they will be shifted? So how much they will be shifted? So you can find here 2 to the power half. That means this is root over 2. What is the value of root over 2? Like 1.4 or something like this. Minus 1 and then root over. So this is the shifting for the second order filter. So this is the shifting of the second order filter. So that means this is 0.4 root over whatever the value, let's say A. So A is the shifting. A is the shifting. So now the value, this multiplied with omega C. So that is the shifting. If definitely this is less than 1. A is less than 1. So the cutoff frequency will be definitely, if I just put a value. So if this is the cutoff frequency for the first order, then the cutoff frequency will be shifted to the left. So this is the cutoff frequency for the second order that will be shifted, because since this is less than 1 multiplied with that one, that will shift it to the left. So your cutoff frequency is shifted. For the third, for the fourth, for the fifth, for the sixth, definitely that will shift it more and more to the value or in different way. No, in third order filter, that will be 2 to the power root 3. So what would be the value? Minus 1, and then it will be multiplied with the first order. So whatever the value, so it shows that your cutoff frequency will be shifted based on the order of the filter, and this is not very convenient for the design purpose. Why? We want to make the nth cutoff frequency should be equals to our actual cutoff frequency. We want to make this one, but due to the characteristics of the passive filter, it is not possible. It is only possible if you put all the resistance and the capacitance are equal in value. So simply by cascading 2 first order filter, we cannot fix the cutoff frequency. It will be shifted for higher order filter. However, by Butterworth filter, we can do so. But introducing the Butterworth filter, we can do so. So then whatever the Butterworth filter, whether this is an active filter or passive filter, the answer is that is of course a active filter. Let me clear those points, how the active filter makes this problem solve. In case of R1 equals to R2 and C1 equals to C2, the transfer function can be written like this, and this is true for all the cases. So we already derived the transfer function before. So if you can remember, this is our transfer function. In this case, we are just putting R1 equals to R2 and C1 equals to C2. If you just do that, we'll find this kind of equation where omega C is equals to 1 over RC. omega c is equals to, so sometimes we are putting omega 0 and omega c are the same, so omega c. So beg your pardon, this is omega 0, not omega c. When we are putting omega 0 in general, this is omega 0, this is equal to actually omega c. Okay, that is the cutoff frequency. Now there is a term we are talking about here. This is Q. Q is the quality factor of a system, or sometimes we are telling that this is a Q point of a filter. So Q is equals to 0.5 for this case. If we compare these two general equation, here we can find that what is Q? Q is equals to nothing, omega 0 by some constant value. What is that constant value? Here the constant value is Q is equals to 1 by 2. Q is equals to 1 by 2. You got my point? This is 2. 2 is equals to 1 by Q. 2 is equals to 1 by Q. So that's why we can write Q is equals to 1 by 2. So for this equation, how we got this equation? This is from the passive element. That means two passive components are cascaded. Okay, we are at that point where R1 is equals to R2 and C1 is equals to C2. And this is all are the passive element. And for that one, we got this equation. Comparing with the actual equation or general equation, we found that omega c is equals to 1 by RC, and the quality, the amount of peaking around the corner frequency. Amount of peaking around the corner frequency is 0.5. I will discuss about the Q. Just to give an idea, you can see this is the pass band, and let's say for the value of Q100, this is the amount of peaking around the corner frequency. So this the corner frequency gets some extra energy due to the value of Q. If you have higher value of the Q, you have higher amount of peaking around the corner frequency, which is not good. For the system. So this is not good. But eventually, this is also not good. At the corner frequency, you do not have any value. That means it is a very sloppy. So it is very sloppy. This is also not good. So that means a very low value of Q or very high value of the Q is not permittable. So what we already derived that for two passive element, two filter using the passive element second order filter, we already derived that the Q is equals to 0.5. So where is that line? Q is equals to 0.5. So this is that line. This is the line. This is very good. Okay. But you can see this is not the best one, because around the corner, they are missing some data. I'm just magnifying a little bit so that we can just understand only let me maximize a little bit. Around the corner, try to figure out around the corner which one is ideal. Which one is ideal to you? Could you please mention the color? Which one is ideal at the corner frequency?
Blue one.
This one? No. Blue
one. Blue one.
Okay. So if I make it clear, to my understanding, the red one is the ideal one. Blue one, still in the blue one, there are some gain in the corner frequency. If you can see, there are some gain. So this was the straight line. If I draw the straight line, you'll see that. Okay. Let me draw the straight line. There are some tools here. Okay. Let me draw the straight line over there. So this is the straight line. And if I put the straight line mostly like this, you'll see there are some corner frequency maybe. Okay, so it is very close to the blue line, but it is actually, if I say this is the corner frequency, this is a cutoff frequency, and the red is the best one. That means it will take all the things in the left side, in the left arena, and they are trying to start to block in the right side. Okay, yes, blue is very close to that one. That means at least we need the red one. Lower than red, this is not good. Higher than red, that is not also good. So that shows that this red line is where q equals to 0.707. So q is equals to 707 is ideal for a filter where the gain peaking in the corner frequency is ideal for the purpose. I believe you understand what I'm trying to make the point here. Okay.
Yes, sir.
Yeah. So now if we move to our original Salenki type. So here we have 0.5. How we got this 0.5? By using two cascading. Okay, by using just two cascading of two filters. So that means you have one, you have another, and you are cascading this one, and they are passive. They are passive element. Now, and that is not acceptable, because as we already know that for 0.5, this is not acceptable. So this is for 0.5, and this is not acceptable because the gain peaking is low. For Butterworth filter, we need more than 0.5. You are correct that more than 0.5, and from the graph we put that, okay, it should be 0.707. Now, which will only possible when there should be some positive feedback from the output. So we need active component. This is very important. That means naturally, if you use a passive component, naturally you can find Q is equals to 0.5. Though this is not true, it should be less than 0.5 because there are some losses inside the resistor and the capacitor. So practically, if I try to build a low pass filter with cascading to low pass filters, the value of the Q should be less than 0.5, though it is, for the ideal case, it is equals to 0.5, but practically it is less than 0.5. So which is not actually the characteristics of the Butterworth filter. For the Butterworth filter, we need Q is equals to more than 0.5, and that is only possible if we just think about this, how we can improve the value of the Q. We need some feedback. We need some feedback, positive feedback from the output. And that's why how we got the positive feedback from the output, we can use a active component by which we can get positive feedback. One such topology by which we can get positive feedback from the output or for the Butterworth filter is called the Salenki filter. Okay, and the name is from the core part of the inventor. So inventor, Shalen and the key. So they invent this sort of circuit. So this is for the, we'll see that this is for the first order Salenki filter, and this is for the second order Salenki filter, where they already introduced the amplifier, the gain part. Okay, so they already introduced the gain part. To my note, I am not introducing the gain part at the very beginning. I am just introducing this part, the resistor and the capacitor and the feedback. And then I will introduce the gain part when it is needed. Okay, so first of all, this is the Salenki filter, and it is connected to the inverting port, and this is a non-inverting port. Gain gets the feedback from the output. So it can be rewrite like this. Okay, it looks very good now. So we have input, we have two capacitors, and this voltage is equals to this voltage. So hopefully you understand this very well. So how this works, and whatever the gain, I put gain is equals to 1 because I didn't put any resistor over there, so that the gain is equals to 1. Let's say the gain is equals to 1. do the calculation yourself, and by doing the calculation, so when you try to do the calculation, you can make, this is an impedance, okay, like Z1 and Z2, just to make the idea clear, Z2, and now do all the calculation afterwards. What is Z1? Z1 is equals to 1 by J, 1 by omega C1 and 1 by omega C2, so something like that. So you can do all the calculations in that way. And afterwards, after doing all those calculations, you can find, our target is to find the transfer function, and we got this transfer function. Eventually, when we got this transfer function, we got a value, the K, which is known as the gain of this circuit. So if we compare with the general form of the equation or the transfer function, then we can rewrite the equation in different way, or we understand that this is the general format for the second order low pass filter. Comparing to these two, we found that the omega C is equals to, again, 1 over R1, R2, C1 and C2, 1 over root R1, R2, C1 and C2. So that is the cutoff frequency. What about the value of Q? So comparing these two equations, we found that the Q is equals to root over R1, R2, C1, C2 over R1 plus R1, C1 plus R2, C2 plus R1, C1 into 1 minus K. So that is the value of Q, where the K is the gain. So K is the gain. By choosing the value of the gain, we can control the value of the Q. So that is the important part. So what is the gain at this moment? What is the gain? For our example, at this moment, what is the gain?
1.
K is equals to 1. We let that K is equals to 1. So if K is equals to 1, this part is equals to 0. And then you can find that what is the value of the Q there. Okay. Now, and you can find the value of Q by putting this equation. And the fantastic thing is, by changing the value of K, we can control the value of Q. Now we need to choose the value of the K in such a way so that the value of Q should be more than 0.5, or you can say Q should be is equals to 0.7, very specific, 0.707 for Butterworth filter. Okay, so that is our target. That is our target. By changing the value of K, we need to control the value of Q. For R1 equals to R2 equals to R and C1 equals to C2 is equals to C, if that is true, then we can find this equation. It's a very easy. Just put those number over this equation. To this transfer function, and you will find this equation. So this is the transfer function where the resistors are equal and the capacitors are equal in value, where omega C is equals to, again, 1 over RC, and the Q is equals to 1 divided by 3 minus K. Q is equals to 1 over 3 minus K. So as I already mentioned that for the Butterworth filter, our target is to put K is equals to 0.707. So K is equals to 0.707, by which we can find what should be the gain. What should be the gain we need, and that is K is equals to 1.586. That is the gain. Okay, fine. Now we introduce the gain control circuit. Okay, now we are introducing. So which one is already introduced here in the book? So I want to introduce now. With the Chebyshev filter, we are introducing the gain factor. Now controlling the value of R4 and R3, of course, you know that we can control the gain. So that is the K part. K is equals to 1 plus R4 by R3, because it is connected to the non-inverting port. So you can find the gain is equals to 1.586. This is the gain. So from there you can find, or you can design your filter. what is the ratio of the resistance R4 and R3. That is nothing but 0.586 for the Butterworth filter. So by taking this gain and the topology where R1 is equals to R2. So we are taking R1 equals to R2 and C1 equals to C2, no problem. Because we have a control over R3 and R4 by which we can control the gain and we can control the value of Q is equals to 0.707. So that means we can have the Butterworth filter with a specific Q factor. So we can choose any Q factor. We can choose any Q factor by choosing the value of the gain. So this is fantastic. So this is all about the Chebyshev filter. Now we can move to the our actual lecture, how that will be incorporated. Now, if we talk about the fifth order filter, so by this time you understand this is the second order Chebyshev filter. This is second order Chebyshev filter. We have already discussed about this, and this is a first order Chebyshev filter. Okay, so altogether second order cascade and the first order, so it will make fifth order filter. Fifth order, which kind of filter? This is a low pass filter. And what is the advantage of this fifth order filter? Your cutoff frequency will remain the same. Your cutoff frequency and the gain peaking will remain the same, because for the first filter, when you design the second order filter, it will restrict this number. For the other filter, it will restrict the same number. For the first order filter, you can restrict the same number. So that means the cutoff frequency will not change their position. And that is the most important part of designing the filter with a cascade. If that is shifted, not a good design. So this is second order and the first order filter. Now, our target is to find all the values. So now you are in the analog domain. You have the topology, you know the cutoff frequency. Now, how to implement that in the analog domain? So determination of the filter component of R and C, how to determine those. So we know that omega C is equals to 1 over RC, and our experience already mentioned that in the market, we can find some minimum variation of the capacitor. So that's why, first of all, we need to choose the capacitor. And based on that capacitor, then we can buy the resistor, because in the resistor, we have a variable resistor. So that's why we choose the capacitor first. For example, if C is equals to, we found 0.1 microfarad. So we can put it there. For omega C is equals to, we already know what is the cutoff frequency from the problem identification, because that is our first part. We need to find the order of the filter. We need to find the cutoff frequency. So whenever we found those two numbers, the cutoff frequency is known to you and the capacitor is known to you. So then you can find what is the value of R. So whenever you found the value of R, that means in this fifth order filter, you know all these values. This resistor, this resistance, because those are the R's. Those are the R's. You know all those resistors. Similarly, we already took the capacitor value, R equals 0.1 microfarad, 0.1 microfarad. So all the resistor and the capacitors are not known. Which one? Just trying to marking those things together, all those components. But what about the gain components? We do not know what are the gain component we should put there. Now concentrate on the gain component. Determination of the amplifier element. So we need to determine R1, R2 for the second order, R3, R4 for the second order, and R5, R6 for the first order. Okay. So from the previous example in the Chebyshev, we can find that this kind of expression we have. The gain, where is the gain? The K. This is the gain. 3 minus K is equals to 1 over Q. So 3 minus K is equals to 1 over Q. So that relation we should remember. From that concept, we can write this for the fifth order filter. How we got this one? 3 minus amplification gain is equals to 0.6 618. So how we found this? If I just go upward, sorry, not more than. So if I concentrate on this fifth order filter, we'll say this is the second order filter part. This is the second order filter part. So if I look at this, so this is the second order filter, where this is the gain part of the system. So comparing to that, because that is the denominators, so we have the gain part is 0.68. So 3 minus the gain is equals to 0.68, as we mentioned here. Okay. Here, this is 3 minus k. 3 minus k is equals to the, what is the number there? What is the number in case of fifth order filter, the second order part, fifth order filter, the second order part gives that value is equals to 0.618. So that's why this is 0.618. This is for the second order filter. If we go back again, what is the second term? The second term is this one. So that means this is the second filter. And the second filter, you'll see that is 1.618. That is the gain part. So if you have the gain part like this, then the second term will come here. So this is 3 minus A2. 3 minus A2 is equals to 1.68. If I make the whole point clear, for this one, this is the first one, where the gain part A1, and we have this relation. For the second one, that means the second circuit, we have the polynomials, and from that polynomials we can find 3 minus A2 is equals to 1.618. That is fully depend on the transfer function. Is that clear to you?
Yes, sir. Yes, sir.
Okay, nice. Nice. Then, where A1 and A2 are the gain of the respective amplifier of the second order filters used, the gain of the first order filter can be chosen arbitrarily. So for the first order filter, you can choose the gain arbitrarily, as it is not dependent on any factor in particular. So they are not dependent. However, we can choose the gain is equals to 1. We can choose the gain is equals to 1 because, okay, why? If I go back to this transfer function again, back to the transfer function, and you'll see that this is S plus 1. So it gives the gain is equals to 1. Whatever the gain you want to choose, you can choose that gain. No problem with that. So if you want to make amplify, but the amplifier, you'll see that the filter is not an amplifier. So if you choose a signal, let's say if you choose a signal, and in the output port of this point, the signal is amplified. It is filtered out, but there is an amplifying factor A still there. Then we need to choose our amplification gain in a such a way so that the output should not have any gain. So that means it should be make a gain like this, so that it will multiply with A, and eventually the gain should be is equals to 1. I believe you understand. So you are giving some input, you get some output over there at this point. We expect that only the filtration will be done. There will be no amplification. But if there are some amplification due to that, by controlling this last portion, we can control that amplification part as well. Okay. Okay, for our case, we can continue. So A1 is equals to 1 plus R2 by R1, and A2 is equals to 1 plus R4 by R3. From this equation, you can find the value of A1 and A2. And from this equation, you can you can find the value, the ratio between R2 and R1 and R4 and R3. And of course, A3, what should be the value of A3? You can choose your A3 value afterwards. So the gain of the first order amplifier, as stated above, can be arbitrarily chosen. Let us choose A3 is equals to 50. So they choose the value A3 is equals to 50. So you can choose any value. If the cutoff frequency, it's very important statement, if the cutoff frequency of the filter is high, if the cutoff frequency is very high, let's say the cutoff frequency is very high. So that means it is very high cutoff frequency, omega C, very high frequency. Then due to the limitation of the operational amplifier gain at high frequency, the gain chosen must be low. What does it mean? If this cutoff frequency is very high, you know that the operational amplifier, where you have positive feedback, they will also give high gain to the high frequency component. So that's why the gain should be adjusted so that the high frequency component will not encourage, or high frequency component will not get some extra advantage. I believe you understand that in case of operational amplifier, due to the positive feedback is not always good. If you have a positive feedback, that also give raise of the amplification for the high frequency. But for the low pass filter, what we want to block the frequency at the high frequency level. But due to the positive feedback, the operational amplifier give high frequency, give gain at the high frequency. That is the problem. That's why we need to restrict our amplification gain. So it actually depends on the purpose. When you design your filter practically, then you can understand. This is the only restriction we impose on the gain of the filter of the first order filter. So only for the first order filter, we can impose this gain. The noise peaking at the high frequency should be limited. So from this R2 by R1, we can choose this value. So it is very much clear what should be the ratio, and similarly what should be the ratio of R3 and R4 from the upper side. I believe now we can design our Butterworth filter, fifth order filter. If we can design fifth order, we can design the sixth order and seventh order, and no problem with that. This example here, we have an example to summarize two approaches given in part A and B. What are the two approaches where the gain could be like this way, or the gain could be in the dB. The frequency could be given in a 25 hertz, and the gain could be given in a number. This is called what kind of number? This is a rational number, or in a dB format. So in the two ways, you can do the calculation. So we have already done this kind of example before. So please go through that. So everything is similar. Everything is similar. Our first target is to find the value of n and omega c. That's it. Afterwards, everything is similar. How to find the pole location, zero locations, everything are the similar after finding the value of omega c and n. Okay, so after finding the omega value and the n value, then we need to move on to the pole locations and the valid pole, and afterwards we can come up with the final transfer function. It can be in the Z domain or it can be in the S domain. So we can put it in the S domain as it is. The transfer function of a fourth order Butterworth filter. So we will not repeat the things. So we have already done for n is equals to 3, third order filter. So here only how they find the pole locations. So I believe that when n is equals to 1, n equals to 2, or n equals to 3, or for different numbers, so you can understand how to find the pole locations. I believe that you can do it yourself. So please go through this and try to design the transfer function for the fourth order filter. And you will find that this is for the fourth order filter transfer function for the fifth order filter. Similarly, where at the pole location and zero locations, so they even not finish yet, because they will follow, that will actually follow the same thing. Okay, so that is all about Butterworth filter at this moment. Yes, any question?
No, sir.
No, sir.
Okay. Okay, now now we can move on to the Chebyshev approximation. So Chebyshev approximation will move on to Chebyshev filter. As I already mentioned, that any sort of filter is an approximation of some mathematical equation, and mostly that is a polynomial equation. So some of the mathematicians introduce some polynomial equation, and we need to fit our transfer function for by using that polynomial equation, and that gives some kind of filter design. When pass band gain contains ripple, we use the Chebyshev approximation. Usually the Chebyshev polynomials are used in filter design when the pass band gain contains ripples, and ripples are greater than plus minus 1 dB. Okay, so this is the polynomial equation. Okay, not the equation, the graph. So I will talk about this part afterwards. Just think that, okay, there are some ripples in the pass band. We have some kind of sinusoidal signals in the pass band, and suddenly there are some monotonous signals. So this is called the monotonous. So sharply it goes down like asymptotes. So this is an asymptotes like this. So suddenly it will goes down like a straight line. So you can think of, if we talk about the cosh function, cosh. So COSH. What is cosh function? When the cos x, what is the maximum value of cos x? What is the maximum value of x? You can put here. What is the maximum value? Maximum value is 1. When this value is more than 1, then it is actually cosh function. This is equals to e to the power x plus e to the power minus x divided by 2. Of course, okay, of course there is x, cosh x. Cosh x is equals to e to the power x plus e to the power minus x divided by 2. So this is the cosh function. Cosh function. And this function looks like this. So this part looks like a straight line. Okay, so this part looks like a straight. So I'll talk about this detail in the extra note. So this is the characteristics of the Chebyshev filter. So what is the characteristics? There should be some ripple, but what about the pass band? What is the stop band? Stop band is almost linear 0. So you are not passing anything after the stop band. And you can have a sharp filter over there by controlling the order of the filter as well. We'll talk about the advantage of the Chebyshev filter over the Butterworth filter. The main advantage of the Chebyshev filter over Butterworth filter is that for a particular value of cutoff frequency, as you know that if I change the cutoff frequency or the sharpness of the filter, definitely if I want to change the cutoff frequency and the sharpness of the filter, we need to change the order of the filter. For a better quality filter, we need to increase the order of the filter. So if I compare the quality of the Butterworth filter and the Chebyshev filter, in that case, if the Butterworth filter need the order of order 5, the same quality filter can be designed by the Chebyshev filter with the order of 3 or less than 5. You can say at least less than 5, not equals to less than 5. So that is the most important and the vital point of the Butterworth Chebyshev filter. And the other thing is that it is not flat. The advantage of the Butterworth filter is that in the pass band this is flat. That means all the components should have the same gain. However, in case of Chebyshev filter, it is giving some kind of ripple, though the ripple value is very small. So it doesn't make any kind of problem practically, but this is a problem. We have the ripple. The advantage is that in the stop band, you are rejecting everything in this kind of case. So this is called Chebyshev filter type. This is type 1. And there is another Chebyshev filter called inverse Chebyshev filter or type 2, where the amplification gain looks like this. It will be monotonous or straight line in the pass band, but there are some ripple in the stop band. Okay, there should be some ripple in the stop band. So this is called inverse Chebyshev filter. So in upcoming section, we'll talk about inverse Chebyshev filter. Now we'll just talk about the Chebyshev filter. Another advantage of the Chebyshev filter is that in the case of Butterworth design, from the given specification, we determine the order of the cutoff order and the cutoff frequency of the desired filter. However, in the case of Chebyshev design, from the given specification, we determine only n, since the specification contains omega c. So here we have an advantage that we can specify our omega c straightforward. So this is an advantage. In the Butterworth filter, we specify omega 1 and omega 2. In between omega c will generate. So that's why you do not have much control over omega c in some cases. But in case of Chebyshev filter, you can start with omega c. So that's why you have full control over the cutoff frequency. For the Chebyshev design, Chebyshev polynomials. So this is the famous Chebyshev polynomial, where Cn is equals to cos inverse omega divided by omega c. At the very beginning, it might looks very difficult to understand, but whenever you go 1 or 2 times, it looks very easy. Not very difficult to understand. Okay, at this moment, this section, I just try to follow the lecture from the DSP lecture of IIT, and I just prepared some lecture notes on for understanding, so that you can understand the things properly, starting with the cost function and designing the Chebyshev filter. Okay, so you can also follow that lecture. So I try to make summarized with different lectures. So I try to make a combination of lectures. So what is a cost function? How it looks like? So this is the equation. If I plot the graph, so this is e to the power x. So I try to plot the e to the power x. The amplitude is 1. So if I put the value of x is equals to 0, that will give the value 0. If I increase the value, so it will increase and goes to the infinity. And if I have x is equals to minus value, and it will certainly got 0 for some value. So it will also goes like this for infinite number. Similarly, e to the power minus x, we got this number. As you can see that this number at x equals to 0 equals to 1. Now, if I add those together, how it looks like? If I add these 2 points, it will gives 1 plus 1, 2. So that's why we are dividing by 2, and that's why the minima is still at the location of 1. So just practically add those together and divided by 2, it will give this kind of graph. So this is our cos x. So how it looks like. I believe you understand the thing. So this is the graph for cos x. Similarly, you can draw the sine hx. So how it looks like e to the power x minus e to the power minus x divided by 2. So these are the two equations. Now you can subtract. If you can subtract, you can find sine hx. If you have cos x and sine x, then you have tan x. You have other trigonometrical terms with x. Another formula, this is we have the derivation, so you can search it and you can find that the inverse of cos x is equals to nothing but natural log x plus root over x square minus 1. So x square minus 1 plus x natural log will give the cos inverse of the x value. About the Chebyshev filter in different way, provide the narrowest transition band. So I already mentioned that the transition band, if I show you, the transition band is very narrow. So here the transition band is very narrow for the Chebyshev filter, comparing with the Butterworth filter. Always when we are comparing our filter with the Butterworth filter. So and this is optimal. Why this is optimal? I already mentioned that for a particular value of omega c and some transition band, if I fix the transition band, what should be the transition band? How we can fix the transition band? Because we know that what is omega 1, what is omega 2. From there we can find what is omega c. The transition band, let's say from omega c to omega 1, we can fix what should be the transition band. For a particular transition band, for a quality of the filter, maybe the Butterworth filter takes some number. The order of the filter is 5, already mentioned, but the Chebyshev filter may take 4 order of the filter. So that means you are saving the order of the filter. That means you are saving time. You are saving money as well. So that's why this is called the optimal filter. This is very popular. Chebyshev filter is very popular. So in different way we can represent, all are the same, but in different ways. So the maximum is 1. So this is just to show the maximum value. This is the pass band, and this is the stop band, and this is the transition band. So this is the pass band gain, this is the stop band gain, this is pass band frequency, this is stop band frequency. Since I followed that lecture, that's why I also followed this notation as well, so that if you can cover that lecture, you find this is convenient or relative. It's a kind of elliptical filter. We'll talk about elliptical filter in future, but optimized, and that is very good at use. So when we talk about the elliptical filter, this is also one kind of elliptical filter, but this is an optimal elliptical filter. This equation is the transfer function of the Chebyshev filter. This is exactly the same equation what I shown here. So this is exactly the same equation, exactly the same equation. So here Cn, so Cn is equals to Cn, and this equation they are putting Cn in this way. Okay, so both are the same. We are putting capital N, and in the book they are putting a small n, but both are the same. So now what is Cn? Here omega is your frequency, the targeted frequency, and omega p is the pass band frequency. So it is mentioned here, the pass band frequency. In the book, if I go back and forth, they are putting omega by omega c. Omega c is the cutoff frequency. The pass band means the cutoff frequency. The pass band means the cutoff frequency here. This p means the cutoff frequency. So here capital Cn is equals to cos n cos inverse x, sorry, cos n cos inverse x for x less than 1. Why? When x is less than 1, x is less than n, then cos inverse, cos actually works as a cos. But when x is greater than 1, When x is greater than 1, then we need cos function. So there is a mistake. X n cos h, there will be h. So there is a mistake. So cos h inverse x. Because what is cos inverse x? Cos inverse 1. What is that? Cos inverse 1?
0, sir.
0. 0. 0. This is integrate. Okay. And what is cos inverse 2? Is that possible? No. This is not possible. When this is more than 1, there is no cos function. Then we need to introduce the cos function. So it will be h. Of course, there is a mistake. Cos h, cos n cos inverse x for the value of when x is greater than 1. When x is greater than 1. When the x will be greater than 1, when x is greater than 1, for this case, when omega is greater than omega p, that means at the range after this. Before this, what is the range? Omega divided by omega p. The value is more than 1 or less than 1. For this range, this is less than 1. For this one, omega means this axis, whatever the frequency. Let's say I am at this point. What is the value of omega? Omega is must greater than omega p. So omega is higher. So that's why this is what? Also higher than 1. So after omega p, everywhere x is greater than 1. So that's why we need to use cos formula to find out the transfer function, and lower than xp, everywhere x is less than 1. So that's why we can use cos formula here, there. So we have cos there and we have cos formula in this case. That's why there are two formulas. And this is the boundary for those two formulas, okay? Okay, so these are the two conditions. And now the objective of this lecture is to give you an idea over this part. So the objective is that how it will start, whether this point will start from this, it might be like this, okay? It might be like this. It might be like this. There might be different combination. It might be like this. So how it will start? Is that depends on the order of the filter, or is that depend on some other thing? So that is our concern. So that's why we just start this portion. Let's say C0x. Need to concentrate, okay, more here. C0x. C0 means n is equals to 0. N equals to 0. For which part we are talking about? We are talking about the portion. We are talking about the portion where omega is less than omega p. That means we are talking about only the pass band. We are talking about the pass band because our ripple belongs to the pass band. So we are here now. So we are there. So at this moment we use all the cos function. We are not going to the cos. When we'll use cos? Outside the pass band. So we are now taking this formula. So put n equals to 0 there. What should be the value? If n equals to 0, this will be cos 0. Cos 0 is equals to 1. Now put n equals to 1. Put n equals to 1. What will be the value? Cos inverse x. So cos inverse x is equals to 1. So we can find it. What is C2? C2, put n equals to 2. So n equals to 2. Cos 2 cos inverse x. Let cos inverse x equals to theta. Cos theta equals to x. So put it there. So cos inverse x equals to theta. So this is nothing but 2 theta. So 2 cos theta is equals to 2 cos square theta minus 1 from this equation. So we can write cos theta is equals to x. So that's why twice x square minus 1. This is for n equals to 2. This is for n equals to 2. So I believe you understand the thing. For n equals to 3, we can find this. 4x cubed minus 3x. To make it generalized, so please go through yourself, okay? Go through yourself. This is a general equation we found for different order of the filter. And we check it for c equals to 3, and we check it for 3. For this general equation, we put n equals to 3, and we found that 4x cubed minus 3x, which is already found there. 4x cubed minus 3x, by which we can validate that, okay, this equation is a general equation. By using this general equation, we can also find c4x in this way. It is not necessary that you need to memorize the general equation. You can do it like this, okay? Whatever we have done here, you can do it like this. But in exam, I will not actually asking this kind of thing. So this is just for understanding, okay? This is just for understanding. Now, in summary, we can write C0x. What is this 0 for? This 0?
N equal to 0, sir.
What is that? What is n? What is n?
N is numbers.
N is the order of the filter.
This is order of the filter.
Order of the filter. So this is 0th order filter. Okay. So this is imaginary. Okay. So this is 0th order filter. Whatever. So this is a n is even. For n equals to 1, you find x. N is odd. For n equals to 2, you find twice x square minus 1, where this is even. For n is equals to 3, we found this. For n equals to 5, we found this. So we just listed, we just try to find that for even function, how it looks like, for odd function, how it looks like. The very interesting thing is that if n is odd, where is those odd numbers? This number, this number. N is odd. If we put x equals to 0, x is equals to 0. Where x is equals to 0? Could you please mention where x is equals to 0? What is x? For our case, x is equals to omega divided by omega p. Isn't it? Yes?
Yes, sir.
Yes, sir. Yes, sir.
So if x is equals to 0, what does it mean?
Omega p, omega equal to 0.
Omega equals to 0. Omega p is already mentioned. Okay, omega equals to 0. That means we are at the DC level. So this is omega. Sorry, this is, okay, this is also omega. So this is omega. So that means you are here. So this is your pass band. So you are at this moment. You are at this moment. So omega equals to 0. That means order, whatever the order, if x equals to 0, then the number should be is equals to 0. Now, if n is an even number, like this, or this. For this, the first case, of course, for x equals to 0, that means if you are at this moment and n is an even number, then what should be the value? For n equals to 2, put x equals to 0. What is the value? Minus 1?
Minus 1.
Minus 1. Put x equals to 0 there. What should be the value? Plus 1.
Minus, these are 0.
Why 0? Put x equals to 0. This term 0, but you have 1.
1.
Okay. So for even function, whether it should be minus 1 or plus 1, and also plus 1. So for even function, you will find plus 1 or minus 1. For odd function, you will find 0. What does it mean? If I have this pass band, I already mentioned that, okay, let's say this is 0, this is 0 line, this is plus 1, this is minus 1. If n is an odd function, if n is an odd function, whatever the number, it can be 7. What should be the starting point? Then what should be the starting point? The starting point should be like 0. Just considering the value of Cn, I'm just talking about Cn. So in that case, it will be like this, okay? It can be like this. You understand? Huh? If this is an even function, like 8, whether it can be a plus 1 or minus 1. Let's say it is a plus 1. If this is a plus 1, then it can be like this. Or if there is a minus 1, it can be like this. You got my point clear?
Yes, sir.
Yes, sir.
There are 3 possibilities. It can start with minus 1, it can start with plus 1, or it can start with 0. If only we are considering Cn. But unfortunately, we also have other numbers in the
It's the
yeah
cost function.
Yeah, we have other number as well. Yeah, we just only talking about this part, and this is a cost function, not the cos x, because we are in the region of x less than 1. But I'm just talking about this profile, how it works. Now it will be multiplied with epsilon square, and there is 1. Depending on those values, definitely the number, the starting point will changes. If this is 0, this is plus 1 or minus 1. Straightforward, we are telling that it will start with 0 or minus 1 or plus 1. That is not true, because maybe that will changes depending on the value of epsilon. Let me show that in detail. Okay, so that will come next. Now we are just concentrating on Cn, how the pattern of the Cn. Okay, so here we are having different color. Let me take a different color like this. Okay, so for C0, what was the value? For C0, this is x, constant. Whatever the value of x, so if I draw this diagram here again for you, the whole diagram. So this is what? This is x, minus 1, plus 1, and this is Cn. Cnx. This is plus 1, and this is minus 1, and this is 0. That's 0. So this is plus 1, minus 1, 0 of the Cn, and this is the x. What is x again? What is x? What is x? Huh? Omega divided by omega p.
Oh,
Why
this
you-
sir.
Oh,
Omega
this
square,
is
omega p.
omega divided by
Exactly. So we are talking about, this is relative frequency. X is relative frequency. So here we are, what is our range of view? Our range of view is from 0 to plus 1. Plus 1 means what? X is equals to 1 means what? Omega is equals to
Omega p.
p. That means you are at the pass band, at the end part of the pass band. What is x equals to 0? You are at
Omega
the
equal to 0.
omega equals to 0. So that is our range of view. Basically, we are concentrating on this range of view. But just to make you understand, we plot it from minus 1 to plus 1. Okay?
Okay.
Because since we are using cost function, what is the range of the cost function? Minus 1 to plus 1. Okay? It can contain. So now, if I have C0, what is C0? C0 is equals to 1. For C0, It is 1.
1.
Go there, yeah.
Okay.
C0 is equals to 1. That means order. If your order is equals to 0, it will be 1. If C1, first order, what is the value?
X.
X. So can you draw that? Yes. For x equals to 0, it will be 0. For x equals to 1, it will be what? 1.
Yes.
So that will be a straight line. So that will be a straight line. You got the point?
Yes, sir.
This is for C1. The same thing I draw here. So this is for C1, straight line. For C2, what is the equation? This is the second order equation, 2x square minus 1. Just draw it. C2, it looks like this. It will be like second order, it will looks like this. So this black line is for C2. That means order is 2. If the order is 2, it will looks like this. That means it actually start with -1. Our range of view, always try to find that this is our range of view. Basically, this one is just for the cos function, but our range of view is this. So for C0, this is a straight line. For C1, this is a straight line from the low to high. For C2, it will be like this. What about C3? This is C3, okay, the green line. You'll see this is the green line, and you can find, let me choose another color. You'll have a maxima crossing to the 0, will have a minima and goes to the 0 again. This is for C3. What about C4? This red dash line, and let me choose that. So it will have a minima, it will have a maxima, will have a minima, and it will have a maxima there. So this is for C4. So you'll see that, okay? If I took the fourth order filter, definitely it will start with this point, okay? It will actually start with this point. So this is for fourth order filter. For the third order filter, it will start with 0, and this will be the profile. For the second order filter, it will start with this line, and it will end it like this. For the first order filter, for the first order. So for the second order is this one, from this to this line. For the zeroth order filter, this is imaginary. We do not know. We do not need to know that. So what are the things? This is for the first order. This is for the second order. This is for the third order. So you'll see how that works. And this is for the fourth order. So what are the starting points? Definitely the starting points depends on what? The starting order of the Butterworth filter. Okay. Now just some analysis or analytical part. So what is the magnitude? The magnitude could be looks like this, of course, by the polynomials, how we set up. So this is the magnitude where we are putting the gain is equals to A, but however, the gain should be is equals to 1. The overall gain should be is equals to 1. So the gain should be less than equals to A, of course, and greater than equals to A by root over 1 minus epsilon square. How we got this? The minimum value of Cn. Try to find that. The minimum value of Cn square. What should be the value of the minimum? What is the minimum value from the graph? What should be the minimum value of Cn square?
1. Minimum value of Cn
minus 1, sir. Cn.
If you have a -1, square of that one will give you 1. So that is not the minimum. The minimum is 0.
0.
Yeah. So you have minimum 0. So that is the minimum. When you have the minimum 0, then what is the number? The total number is 0.
Yes, sir.
Yeah, total number is 0. And what is the amplitude in that case?
Amplitude.
Yeah, minimum for the minimum number.
A.
How you got that?
Cn equal to 0. তাহলে এই পার্ট ক্যান্সেল, তাহলে 1 এর উপর রুট
Exactly.
করলে 1.
So this part will cancel. So this is 0. So that's why the gain is A. You will have the gain is equals to A. And what is the maximum value? The Cn
1.
square. Yeah, the maximum value is 1. That's why this 1 into epsilon square, 1 plus epsilon square to the power half. So that is in the denominators, and the numerator is equals to A. So that is the maximum value. So our magnitude response should be belongs to this. So now we can understand what is the minimum value and what is the maximum value. However, we try to make the A is equals to 1. Then we found that the range of magnitude response is from less than 1 and greater than 1 over 1 minus epsilon square. So that's why we are writing in this way. So there are two lines in the pass band, and there are some ripple. Okay, whatever the ripple is, that the maximum value is what? 1. This maximum value. And what is the minimum value?
0.
1 minus
1 divided by 1 minus epsilon square, and then root over half. So that is the range. Okay, so that is the range. So ripple will goes up to higher value 1, and lower value, what is the lower value? 1 minus epsilon square to the power half. So that is the conclusion we can turn off. So by which we can understand this very easily. So what should be, how it should be looks like. Okay, if I draw it for you again, we are just talking about what? Only the pass band, So let me choose another color, black color. So for first order filter, you understand that it will start with what? Let me give you this clue from the upper side. From the first order filter, it will start with 0.
0.
Okay, good. It will start with 0. Then if it is 0, if this portion is Cn is 0, Cn square is 0, then what should be the starting point of the amplitude? Let me write it like this: A divided by what?
Just
1.
A.
A divided by 1, because this whole portion is 0. 1 to the power root is equals to 1. A divided by 1. And conventionally, what is the value of A? We put 1, isn't it? If you have any problem, just ask me.
Okay, sir.
The gain is 1. A is equal to 1. So what should be the starting point for the first order filter? It will start with 1. 1. And this is 1 divided by 1 minus epsilon square root over. Okay, just take it like this. Okay. So it will start with 1, and it goes straight to this up to omega p, straight line. You agree with me?
Okay, sir.
Yeah, because this is a straight line increasing, so that will straight line decreasing. Is that okay?
Okay, sir.
Yes, sir.
Okay. And then it will suddenly goes down. Okay, good. What about second order filter? Here you can see for the second order filter, which one is the second order filter? This black line is the second order. It is -1. Cn square is -1. Sorry, Cn is -1. So Cn square is what? Plus 1, isn't it?
Yes, sir.
So then what is the denominator? 1 plus epsilon squared to the power half. So that will start with 1 plus epsilon to the power half. Is that okay?
Yes, sir.
Yes. So that's why they will start from there. Let me choose another color, green color. So that will, and there is a, looks like a sinusoidal, and then they will jump back to that one. So this is for the second order. What about the third order filter? Here it will start with where?
0.
0. 0 means what? Here it should start with 0 means 1.
0 is 1. Yes.
0 means 1. If it is 0, then automatically it will goes to like this 1, and
1.
we can see that, and that's why it starts with 1. So this is 1, but this is what is the order we are talking about? This is for, this one is first order, this one is second order, and now which order we are talking about? Third order.
Third order.
So that's why you'll see that there is 1 maxima, 1 minima, 2, 3 maxima, and then goes down. So the order of the filter will give you the number of maxima and minima. For the second order filter, you have a minima and a maxima. For second order, third order filter, we have 1 maxima, 1 minima, another maxima, and goes down. So this is for the third order filter. What is the fourth order filter? I already mentioned that it will start with 0 and 1 minima, maxima, minima. So let me choose another color so that you can understand. Minima, maxima, minima, maxima. So 1, 2, 3, 4, and then goes down. And when you increase the order of the filter here, I just try to make you concentrate here. When you increase the order of the filter, it will also increase the quality of the filter in that case, that in a way that the pass band will goes narrow down. The transition band, not the pass band, sorry, the transition band goes narrow down. And that is how the order of the filter will give high number of ripple, but narrow transition band. So you have advantage, both advantage and the disadvantage of the higher order filter. Is everything clear to you?
Yes, sir.
Yes, sir.
Okay. Nice. So it is already mentioned there. Okay. I will try to jump very quickly since this is the difficult part. So this is vague. Okay, this is vague. So this is not true for all the order. So for different order, the starting point will be different for this kind of filter. Okay. So I hope that now you can understand this very easily. Where in the lecture, where omega, I mentioned omega is equals to your omega. Take it like this, and omega c is equals to omega p.
Yep.
And that will actually help you. And small n, there we use capital N, and that's it. So we use this kind of thing over there. And I took that lecture part from most of the part from the IIT lecture, so you can also follow that. He's a very good person to follow DSP and the other things. I encourage that, those video lectures as well. Okay. So in the log format, we can also do the same thing here. And remember those equations, okay? It will help you to understand the process. Now, step-by-step design of the Chebyshev filter. So make your mind clear. Whatever we have done, just to make the idea clear, now we will do step-by-step calculation for designing our filter, okay? So what are the parameters should given to us? H1 omega. What is H1 omega? There are two terms. So H1 omega should be given to us. The pass band gain. The omega 1. That means now this is omega 1 is equals to exactly omega c. Omega c should be given. So this is omega c. Omega c should be given. The gain should be given us. And omega 2. This is the attenuation band. So omega 2 should be given. So this is omega 1. And what is the gain at H2? That should be also given. So these 4 parameters we need: H1, H2, omega C, and omega 2. If we have those things, we can design our filter. So the design process is illustrated here, so I will not go into detail, so you can go for that one. You need this formula to understand, so just writing here: cos inverse x is equals to x, cos inverse x is equals to ln, I already mentioned, x plus root over x square minus 1. So you can also draw this in the MATLAB so that you can understand the plot very easily. Okay. Step by step, you have this fundamental equation, need to memorize this. Okay, so this, because this is the polynomials, that is the starting point. As we have H1 and omega 1, omega 2, there should be 2 equations like the previous one in the Butterworth filter. By using those 2 equations, straightforward, we can find the cutoff frequency, we can find the order of the filter. Okay, straightforward by using equation, the same equation, 2 unknowns. What are the 2 unknowns? Omega C is basically given to us. This is not an unknown. We need to find only the value of n from this. This is a single unknown. However, Cn is also unknown in the equation. So that's why there are 2 unknown. One is n and another one is Cn. And we fortunately have 2 equations as well. From the 2 equations, we can find these 2 unknowns. Is that clear? Just follow the process. It's very straightforward. For the decibel concept, okay, you can go through that. It is very straightforward. Now, determine the poles. Okay, this is what is the first step? First step is determining the order of the filter. What is the second step? Determine the poles, or you can say the determining the pole, not the transfer function. Okay, there are different steps to determine the poles. Just be with me. You need to memorize something, but be patient. Okay, so because this is very important. First of all, rule number 1. First, from the given specification, we determine the valid Butterworth poles. Can you determine the Butterworth pole? Are you confident? Yes. From the last lecture.
Sir, in previous
last
lecture, yes, sir.
Yeah, so you can do that. So you can determine the Butterworth pole easily. So let's first determine the Butterworth pole. So this is rule number 1. Number 2, determine the factor k from the expression. So we already know what is epsilon, where we know the epsilon. So let me just clear that one. So here you'll find this epsilon from there. From the equation, you'll find the value of the epsilon. Okay, so this is epsilon is known to you for the value Cn is equals to 1. So I mentioned that Cn is unknown, but Cn is known for the value of, when you know that omega p is equals to omega c. So at that location, of course, the value of x, you know the value of x, and in that case, you know the value of Cn. So it is already mentioned there. So how Cn is equals to 1. So it is already mentioned there. Cn is equals to 1. From there, you know already what is the value of the epsilon. So you know the value of the epsilon, you know the value of n, so you can determine the factor k from this equation. Find the tan hk and cos hk or cos k. Okay, so this is rule number 3. Multiply the real part. So in this equation, so you already have your Butterworth filter pole location. Multiply the real part, A and C. Multiply the real part with tan hk This is called normalization. Normalization Butterworth poles are, so this is actual. This is actual. Now normalization, A should be multiplied with tan HK plus JB, and C will be multiplied with tan HK plus JD. Okay, in that way you may have another poles, so you can carry through. If you have any problem to identify, just let me know. Rule number 5, now denormalize the pole by multiplying with cos k to get the desired Chebyshev filter. So at this moment, you will get actual Chebyshev pole. Thus the Chebyshev pole are, now this is the whole equation. You already found the value of A and B from where? Butterworth filter. Then you found the value of K, and now you are multiplying the whole factor. Now you are multiplying the whole factor with cos HK, cos HK. So these are now there are single pole, and this is a single pole. So you have two poles in the equation. So now those are what kind of pole? They are the Chebyshev filter. So we now use this rule to determine the Chebyshev poles of the given example. So for a given example, in our example, we have n equals to 4. So in the upper example, and for the Butterworth, so let's say for the Butterworth pole, we found n is equals to 4. So it is very easy, convenient that you found the pole locations. And since omega c is equals to 150, so you'll find what is the value of B1 and B4, B2 and B3. So whatever B1 and B2, B4 and B3. So let's say these are the poles. So we are talking about the Butterworth filter. So this is how they are representing. So B1 and B4, B2 and B3. So those are the pole conjugates. Okay, so they are conjugates. So you need to know, of course, there are some dummy poles are there. So what is the order of the filter? What is the order of the filter?
4, sir.
4. Capital N is equals to 4. So capital N is equals to 4. So they are the dummy. So we are neglecting this one. So those are the 4 poles. These are which kind of pole? These are for the Butterworth filter. Now this Butterworth filter will be converted to the Chebyshev filter. How? So I can just move forward, and this is the final equation, C1 and C4. So how you can find that? This formula is there. This formula is there by which there's a plus, you'll put plus minus, there's a plus minus, by which you can find the 4 locations. So these are the 4 poles you can find. This is 2 and this 2. And if you plot this in the Z domain, if you plot this in the S domain, sorry, we are in the S domain. If you plot, it would looks like elliptic. Now it is not a circle. It will be converted like a elliptic one. So now let's say this is C1. Let me choose another color. Just approximately. This is C1, C2, sorry, C4, C2, C3. You got my point. So now B1 is converted to C1, B2 converted to C2, B3 converted to C3, and B4 converted to C4. And it looks like an elliptic. And that's why it is also known as an elliptic filter. It's a kind of elliptic filter, but since this is a special filter and people like this, and that's why, and there is a different scientist give this polynomial whose name is Chebyshev. He's not an American, he's a person from other country, maybe from the Russia or somewhere else. And the name what we are writing here, Chebyshev, the actual name is different and very difficult to utter. but the Americans give this name Chebyshev for simplicity. Is this concept clear to you?
Yes, sir.
Yes, sir.
Okay. Right. Now, this is not the end. We are just finding the pole location. Now, the step number 3 is we need to find the transfer function. To find the transfer function, this is the transfer function. Now here P is a new term. We already found C1, C2, C3, C4. What is P? Nothing very special. The modulus value of multiply C1 with C4. And you see that there is a curly bracket. And afterwards, we have modulus value of C2 multiplied with C3, make multiplication, and then we are multiplying these two. So in the denominators, we can find it very easily. We found the denominators, and we try to find the value of P. So they are finding P1 first. So this is P1 and P2, and then multiply both together. This will give you a real number because we are taking the modulus value. And at the end, Alhamdulillah, we got our transfer function. If we have the transfer function, we have everything. So we can plot it in the frequency domain, and we can analyze the filter. Okay. So comparison between the Butterworth and the Chebyshev filter. So you can compare. So I already talked about this. Just go through this, and you'll find there are some examples. This example is very easy. Easy and important for your exam. You may face this kind of problem where they are comparing design a Butterworth or Chebyshev low-pass filter for following specification. So you have a specification for which you need to design both Butterworth and the Chebyshev filter, and then you need to compare those filters. Okay, you need to compare those two filters. And please go through this, and it will end the chapters. It will end the chapters. And let me introduce one software to software. Okay. Restoring the annotation bar. Okay. Probably you can see the plot. Can you see?
Yes, sir.
Okay. So this is a free tool in the online. You can find it where you can play with. Okay. So if I took a Butterworth filter, so before going to the Butterworth filter, let me choose a blank filter. So you can click there and drag it to this Z domain. So so this is a blank filter. In this case, this is a transfer function. It's give a graphical representation of the transfer function. And this will give you plot magnitude response, phase response. Here, it represents the time domain representation and circuits. Okay, let me give you a very simple example of if I put a real pole, 0 and real pole. I'm just designing a low pass filter. Okay, I'm designing a low pass filter. You can see this is a magnitude response and how it looks like. Let me give this transfer function. How it looks like, low pass or high pass filter?
Low pass
filter.
Low pass filter. So you have a low pass filter. Now if I change the 0 location, and you'll find that this is a high pass or low pass filter. high pass filter.
High pass filter.
High pass filter. So this is the way how you can find this very convenient. So I'm selecting this one. So this one is giving the highest magnitude. If I select this one, it will give the magnitude response. This will give you the phase response. So this is the phase response. For FIR filter, this is an FIR filter. You'll find the linear phase. You'll find linear phase response. Can you see that? If I block this is the phase response. Is that linear or non-linear?
It's linear.
Linear. If I change the pole location, can you see? If I change the pole location, it will be a non-linear.
Sir.
Can you see that?
Yes, sir.
Yes, sir.
If I change this, it's a non-linear. And similarly, you can see the time domain response here. It's very convenient. The time domain response, you can see the time domain response as well, conveniently. Similarly, you can see in this platform, you can see the Z transform value. Z transform value is given. The circuit components are given. If you want to have code, you can click the code, and C code is also generated here. So this is C code. So you can take it and burn it to the DSP board, and you can also implement your filter. So you do not need to even write the code here. So the code is also generated. So this is a very fantastic tool. Okay. So now if I want to design a band pass filter.
Sir.
Yeah.
এই সফটওয়্যার ফ্রি মানে ডাউনলোড করে নেওয়া যাবে?
This is not downloadable. This is in online. I'll give you the link. Okay. micromodeler.com/DSP. Okay. I just searched it and found it. Maybe there are some other tools as well. Okay. If you find better than this, just share with me. No problem. The real pole, I just put another real pole. And now if I move to the magnitude response, you will see that, okay, this is a band pass filter, isn't it? Band pass filter. I can change the quality of the band pass filter by changing the pole location. See the time domain response, you can see the circuit, everything is possible here. Very, very convenient. Now, since we already know about the Butterworth filter, I just put a Butterworth filter. First of all, a blank filter, let's say Butterworth filter. So they are putting a Butterworth filter with a lot of orders of the filter. So how many poles, how many zeros, okay, they are just giving it like this. Okay. So the pole locations and the zero locations are given like this. Okay, let me. So this is a Butterworth filter. They already give us. And this is the conventional one. So this is the green line shows what? What? What is the green line?
WC.
Cutoff frequency. You'll see that here in the right side. Right side, can you see? This is the order of the filter. Okay? I change the cutoff frequency higher or lower. And the order of the filter will remain the same. You can change the order of the filter. That will give advantage. But here we are not changing the order of the filter. You can implement more poles and you can change the order of the filter. Okay? And if you want to see the transfer function, it is very convenient. Okay? You'll see where at the zero location. So this is a zero and the poles are there. If you change the pole locations, okay, I'm changing and the pole locations will definitely changes. Yeah, you see the pole locations. You can magnify and you can see the pole locations. You can see, and the time domain response. You can see the circuit as well. There's a very complex circuits. Let's say we'll have. Okay, so this is a very good tool to play. Okay, isn't it?
Yes, sir.
Now, if we go for Chebyshev filter, what we already found, the Chebyshev filter. So this is the Chebyshev filter. You'll see there is a ripple. if I magnify this is the ripple. This is the ripple you can find. If I go back, you'll see the ripple. This is the cutoff. I change it. This is the ripple side. You'll see the ripple. And you see the pole locations and the pole locations, how the pole locations are changes. So you can change the pole location from here, okay? Or you can change that by this. Okay, very convenient. You can design your filter with a click of this. So how easy it is. So now if I introduce, okay, let me introduce some poles here arbitrarily. So I want to introduce complex pole. So I'm introducing complex pole there. Okay, hey, I'm introducing complex pole, artificial. Now can you see the changes? So by changing this one, I can just interrupt. Okay, so what could be my desired filter? So it looks not very good. Okay, so I can change it. So always filter design is a trial and error method. Always filter design is a trial and error. Let me think about this. I want to do this. I want to do this. And maybe it is more convenient like this. Do you like this? Yes, I like this. Because the ripple is low now. Can you see that? I introduced two poles. Now the ripple is low than the previous one. You agree with me?
Yes, sir.
So by changing this pole location, can you see that? Yeah, I can change it like this. I can change it like this. So which one is convenient to us? Okay, let me choose that one. And there are some other tricks as well. There are some video lecture. When you just open this, there are some video lectures. So by which you can find some other interesting points. That means you can also set some points. Can you see that? I can choose this.
Yes, sir.
This. So you can set some points as well. This is very good. Okay, nice. So I want to finish the lecture up to this. So maybe from next day we will talk about the chapter number 10, and this is about step-by-step design of IIR filter. So we start our IIR filter in the next day, but I will upload this chapter, okay, today. I will upload this chapter so that you can go through that, and we need to finish everything very quickly because we need to evaluate the process. As you know that our evaluation process should be finished by 14th of September, okay, 14th of the September. It is extended. That's why I would like to give you the time for the Viva and the final exam. Viva and the final exam. Let's say this is the date you can fix. So do you want to give the Viva and final exam in 2 days or a single day?
2 days হলে ভালো হয়।
Okay.
প্রিপারেশন বিষয় স্যার, এই ক্লাস লেকচার গুলো যদি আমরা হুবহু ফলো করে যাই তাহলে তো মোটামুটি হবে আগে বই থেকে স্যার।
Okay, let me end the lecture first. So thank you for joining for this lecture, and